Thank you. Thank you all for coming here. Thank you, organizers, for remembering my name as well. First, I would like to talk about some tree construction for Koszul-Tate resolution. But first, I would like to remind you all what is Koszul-Tate resolution, something that you all have seen maybe at least once, or seen maybe in the previous millennia, century. So let me outline this construction. So I would like first briefly, it's a Koszul-Tate resolution. Right, so the input, so as in the original Tate's paper, so you take some R to be a commutative Noetherian ring. Okay, and some ideal I inside R. Right, and the output of the construction is some free differential graded algebra A equipped with the differential delta, which I will specify below, right? And the A is freely generated as some symmetric tensor algebra of some R module epsilon. And this module epsilon is positively graded, so I can write it as sum epsilon 1 plus epsilon 2 plus so on. Yeah, and in this construction, each epsilon I is finitely generated. Okay, and the other property that this differential graded algebra should has is that maybe I should move it a bit up. Right, that the homology of the differential delta should be 0 for all positive I, and integrally 0 is just R over I, right? And of course, there is an algorithm how to arrive at this resolution. I mean, it's not so complicated. And I would also briefly outline it, just to have it on the blackboard. It's so the step 1. So let us fix the generators of ideal I. So let us fix the generators I in some set, some finite set J. Maybe let's put J. Right. So the ideal I is just J. Yeah. So once you fix the generators, you say that the epsilon 1 is a free R module generated by J. So it means that for any element x in epsilon 1, you can write x as a sum xi, I, right, and I is in J. Right, so it's a free R module of a rank J of rank J. So J is a number of generators. Okay, like the first step, and the differential is defined in such a way that the generators of E1, they just reproduce you the generators of ideal, right? So delta is defined from epsilon 1 to R in such a way that the element I goes to just the generator phi. Right, so it's like first step of the construction. So the second step would be, okay, the prolongation of delta. So let us extend the differential delta to the algebra, the symmetric graded algebra of epsilon 1, right, as a derivation. And let us look at the H1 of delta. Yeah, so unless you are in the case where the ideal, the sequence of the generators phi j is a regular sequence, the homology might be not zero, so you need to find some representative of this. So let me call it maybe phi j prime, right, such that j in some j prime, some generators of this homology. H1, yes. H1, yes. So let us find some generators of this. And let us construct the free module epsilon 2, right, which is just generated. It's a free R module generated by J prime, right? What?
And S is symmetric algebra or SR?
Yeah, it's graded symmetric. So
okay.
I mean, like for two elements in,
so you first
have xy
you
equal minus
first have a set. The set give you a module, then you use symmetric to generate to algebra.
Yes.
Thanks.
Mm-hmm. Okay, so you constructed epsilon 2, and then in a similar way you extend delta. So delta from epsilon 2 to epsilon 1, right? You get element some j prime, it goes to phi prime j, right? Then you extend this delta, extend delta as a derivation to s of epsilon 1 plus epsilon 2, right? And well, that's almost like the whole story. And on step 3, you repeat this construction at degree 2. So again, you find the homology in degree 2. You construct epsilon 3. Yes, yes, and so on. Yeah, so the additional, maybe the additional terms, I mean, like to put all the cohomologies to 0, I introduced these elements of this free module of degree 2. Right. Yeah. No, I don't think so. I don't. It's actually it's the whole thing. Yeah.
You only care about the homology in degree 1?
No, I care about the homology of degree 2, but the point is...
No, I mean, as R of P, if E is concentrated in degree 1,
yes,
has all gradings, 1, 2, 3, everything.
Yes.
And what kind of grading do you care about here?
Yes, so well, once I introduce the module epsilon I care about the homology in degree I.
But, so all the higher degrees you just dismiss?
Yeah, or you don't look at it.
Yeah, because you look at them at the next step.
Just to be clear, so what you're doing on the second step, which is the second step, is you choose generators for E2, like arbitrarily, I suppose?
Yes.
And then you say, I'm going to send, like, well, what are you doing actually? So what?
Yes, so you find some representative of the homology.
Of the homology.
Right, so it's...
This is choice. You have a homology and you choose representatives in the...
Oh, okay, but you said that they generate, E2 is generated. Are you talking about each one is generated?
So, Okay. You find the representative of H1 in S of epsilon 1, a degree 1.
Okay.
Okay? Yeah, so this is some module, right? And it has some generators, finite number of generators, because of the Noetherian property. Yes.
H1 has it as generators or E2?
H1.
Okay, yeah.
H1, yes. So, and then I construct E2. This is just a free R module. And the number of generators is the number of the generators of homology. That's it.
I get it.
Yeah. That's just it.
It's cocycles.
So, let me maybe just say a few remarks about this. So first, yes. So if the sequence Fj is a regular one, right? So the regular sequence, so the sequence F1, Fr is regular. If Pi plus 1 is not a zero divisor in R modulo Phi1 Phi, right? So if the sequence is regular, for example, if R is a polynomial ring and you take the first k variables, right? Then, for example, this is a regular sequence. In this situation, the construction stops actually at the level 1, right? And if it's not regular, then in general it's not clear, right? So we struggle to find any like Koszul-Tate resolutions like which are explicitly constructed if the ideal is not regular, right? So this algorithm actually we can work with it only in very specific situations, it seems to me. Okay, so this is what I wanted to say about the Koszul-Tate differential Koszul-Tate resolution. And yeah, so and maybe another remark, like why am I telling you this? Why do I care about it? I mean, it's not only about filling the blackboard with some writings on it, right? It's because I mean, in the end, we want to construct some BFE charges, right? So in the end, we would like that R to be not some just Noetherian, but also has a Poisson algebra structure, right? And for this, it's always nice to have a Koszul-Tate resolution. Okay, so in case the generators of ideal are not regular, or in physical language, if the constraints are not regular, then I mean it's hard to implement this construction. What is good though is not a Koszul-Tate resolution, but a Moji resolution. Right. So the setting is as on the previous board. So we still have commutative Noetherian R, some ideal I. But now I want to resolve it just as a R module. So I want to resolve R over I in R modules. So let me write these complexes. MD. So M is a free R module, positively graded, right? And M is M1 plus M2 plus so on, and each Mi is also finitely generated. Let me. I will tell you about this. Yeah. So the point is, once you have this resolution, right? K 2 1 R. So for D also you have the same property. So the H0 of D is quotient R over I, and in higher degrees the homology is 0. So the point is, in a much bigger variety of examples, this resolution is finite. So, for example, if R is again some polynomial ring, and I is any ideal, not necessarily which is generated by a regular sequence, like any sequence, right? So if R is some polynomial ring in n variables.
This one is R mod J.
Sorry, could you repeat the question? I don't hear.
Is the first one R mod J?
Can you put the mask away, please?
The first short question. The first one is R mod J or is R?
R mod I.
I and J are
Oh, yeah.
equivalent for him.
Okay.
This is I, right? It's R mod I, not J.
Yes, it's I.
Maybe you're correct.
It's I. And this is I. Yes. Okay, so if R is polynomial n variables, then you have this famous Hilbert-Syzygy theorem, right? That states that the modular resolution of R over any ideal I has length at least n. So at most n, yes, sorry, most n. Yeah, so in this sense, the modular resolution is something that you can construct in particular examples in comparison to the Koszul-Tate resolution. So this is like one story, one classical story, and then I want to tell you now second one, because I mean in the end what I want to do, I want to construct the Koszul-Tate resolution using the modular resolution, the finite one, in a finite number of steps. Like this would be the goal in the end. And with the algorithm that is on the upper blackboard, is not clear how to do. So, and I will also give some examples. And in order to find the algebra resolution in a finite number of steps, I need another input from previous century. So, yes.
So I just wanted to say before, you see, you have the cohomology to calculate at each degree. And not only you have to make this calculation, and then you have the choice of choosing representatives in the algebra. And so you have to do that each degree, and it's really getting horrible in practice, but even it's not stopping. So it's an infinite number of steps you need to do in general. So that's what we wanted to avoid.
Yeah, so let me maybe explain something to you about the trees. So what I mean by trees, so it would be some k-vector space of planar rooted trees. So let me maybe write tree, some tree. Okay, so the tree would have root. Tree also has some, here it's inner vertices. Some inner edges. And leaves, of course, right? So this is leaves. And the point is, it's not difficult to equip the tensor algebra of trees with some differential partial, such that it is a DGA. I'll explain how. and homology of partial is 0, so I greater than 0, and in 0 it will be just k. Yes, so and first of all, so let me maybe, before I even talk about the differential graded algebra of these trees, let me introduce the grading here. So if I take a tree T with n leaves and k inner vertices, then degree of T is just the number of inner vertices plus number of roots. So root is 1. And also I forgot to mention that this space of planar rooted trees, I would like to also extend with a trivial tree. So trees of this form plus this tree, which has no root, just one leaf, and that's it. And moreover, one more property I forgot to mention about the valency of edges and root. So so it's assumed that the valency of root is at least 2. So at least there are 2 inner edges that are coming out of it. And for inner vertices, at least 3. So there is a 1 incoming and at least 2 outgoing. Yes, what was the question? Okay.
So
Yeah, it's okay.
it can only be one root, right? So only one root, right? So
Yes, so root is either 1 or 0. 0 for trivial trees.
oh,
So I wanted to extend these trivial trees. I forgot to mention in the first place, but
Degree is 0 for 0, 3.
yes. Yeah. And how the differential works? So first in a trivial tree is 0. And on other trees, so it's called trees of degree greater than 1. Delta, you have 2 components. Right, so yeah, so because the differential, it's enough to restrict delta to just 2 trees, not to the tensor product of them. So the first component would go to the elements in tensor algebra of trees of arity at least 2. So elements where there are at least two different trees. And the second component would go just again to trees. Let me maybe call it delta up component, delta down component. Okay. And let me define it first recursively, then explicitly. So first thing first, I would like to introduce first some natural operation on these trees. So if you have tree T1, Tk, k greater than 2, then I would like to introduce this natural operation of joining trees into one tree. So you have a tree T1, Tk, and I want to map it to tree T1, Tk, joined by one root. Right, so I would call this operation R root. So this is operation of degree 1. Trees for the trivial trees, for example, they are mapped to this first non-trivial tree. And trees, for example, like this, they are mapped to this tree. Okay. Then the differential looks as follows. So the delta up component is just R minus 1. Okay, so you take a tree, for example, like this one, and it goes to just just 3 trivial trees. And the delta down component.
You can do that to any tree.
Hmm?
What do you mean -1? I mean, there's not an injective map.
So if k is greater than 2, right? So any tree is 1-to-1 to the trees in the tensor algebra of degree -1. So you can take any tree, right? Let's call it maybe T1, T2, Tk. So these are just some subtrees. And what you can do, you can remove the root. And if you remove the root, you end up with just k trees, right? And if you have k trees, k greater than 2, you can join them with root. So it's 1-to-1. So the only problem if you have one tree, I do not allow this operation. But for if you have 2 or more trees, then it's okay. And the down component is recursively defined as follows. So first you unroot. You apply previously constructed differential delta. You project to the subspace of trees where there are at least 2 of them. So the elements of arity are at least 2. And then you root again and assign minus.
Just wrote them next to each other.
So what?
Well, when you wrote in -1, I mean, you get a tuple of trees. So are you adding them, or what are you doing?
No, you get an element in the tensor algebra, like of arity. So like.
Okay, you're
like
putting a
this.
tensor between them.
Yes. It's not 3 trivial trees. It's 1 tensor 1 tensor 1. Okay.
It's a vector space generated and so on.
Okay.
Make this clear.
Yeah. And yeah, so yeah. First of all, if you look maybe closely enough at the definition of this differential, you can see that actually from here it follows that D with projection 2 R plus sorry, root. Yes. So I will give I just want to make this small comment, and then I'll explain. So P greater over 2 is a projection to the space where there are at least 2 tensor trees. So the symmetric algebra of trees, right? It has just trees, tensor trees, and so on. So P greater than 2 is a projection of the tensor algebra of trees to elements which has with trees tensor trees plus trees tensor trees, and so on. It's not symmetric yet. It's not symmetric yet. No. So trees plus trees tensor trees plus so on. Yes, second and higher. Okay, second and higher. So yes. Yeah, that is correct. So from this definition, if you maybe look a little bit closer to it, you find this nice thing. So if you degree greater than 1, it's 0, right? So there is like contracting homotopy actually here with the definition given like this. So indeed, sorry, partial. So sorry. Yes, so indeed it would be it's a DGA with the homology equal to 0 in degrees higher than 1. So let me maybe explain how this delta works. So it's not give you not just a recursive definition, but actually like for any trees, how would it work? Let us maybe draw a tree again, like this. So with tree T. Oh, and how delta acts on this tree. So first, of course, you have this unroot operation all the time. Delta up. So you get trees like this. Yes. And plus the following thing. I'll explain in a moment. So a inner vertices. And here I would like to write this. So, for example, here it's A. It's the inner vertex A, and I contract the edge that joins A with its parent vertex. So what are the components? So first, it's this unroot operation. So you just remove the root, and you get tensor product of at least 2 trees or higher. And the second component is you remove inner edges. So you identify some inner vertices with another inner vertices. And the weight, it's calculated as follows. So you start from a root. You draw a path from the root to the vertex A, and you calculate the amount of vertices on the root plus the amount of vertices to the left. So in this case, let us calculate. So the amount of vertices on the root is root plus this, so 2 plus 1 that is to the left. So it's 3. So this would be actually in this case WA would be 3. Yeah. So and this would be the following. Plus A minus. So this is I calculate for A here. Then let us calculate when A is this vertex. So this would be again 1. So again minus. And this would be like this. This tree. Yes. So there are 3 terms. So I count all inner vertices A. So it's here, here, and here. Okay, and you can. So the first term you construct this one. It's written here. Then the second one you construct here. It's this one. Yes. Sorry. Yeah. Sorry. You're correct. Yes. And the last one is constructing just here. Okay, so you get. Yes. Yeah, like this. Yeah. Sorry?
The rule for WA.
Yes.
What is it again?
Yes. So WA is just a sign, which is it's a number of vertices from root plus number of vertices left to the root, to the path. That's it. Okay. So this is how delta works here, and I mean, I personally like to explain starting from here, but actually this construction it doesn't come from nowhere, right? So actually, I mean, in the literature, you can find this particular construction. So this DGAT of trees with the differential delta as a bar construction of the so-called space of bracketings. In our words, it's just over K with some a infinity co-multiplication delta. So in this case, what does it mean? That I mean, actually, this whole construction is come from the trees, but where you choose the different gradients. So not just a number of inner vertices plus root, but actually you again add +1, and there you get some. You can view this operation as a co-multiplication, right? So for example, here there will be like operation from a tree to two trees, right? And the fact that they all combine in a nice infinity coalgebra, it amounts to the fact that here it's a differential. But just for those who are interested or know already from where does it come from. And so let me maybe just say what do we want in the end. So we want to combine these two things. So I would like to combine the module resolution that I have here. So assuming that it is finite, so of some, not just notarial ring, but actually some commutative algebra R, ideal I. So I assume that the resolution is finite, and I want to combine this tensor algebra of trees. So in some sense, what I really want to find, what I want to present is so it's not a resolution of sorry. H0 of D is R over I. So this part is not exact. Or if you prefer to write, you can write it like this. Okay. Yeah. So what I really want, I want to find a suitable way how to combine this plus this trees and partial. So to find some algebra resolution of R over I with again, so with the property that is generated by some modulo epsilon, and yeah, and I would like to do it in a finite number of steps in comparing to the Koszul-Tate resolution, but there will be, of course, price to be paid. Okay, so let me maybe start. First thing that I would like to explain here, it's decorated trees. Yes, so one natural thing how to combine both trees and the module resolution is to actually start decorating trees, right? So let me maybe write trees first as a sum of trees n. So trees n are trees with n leaves. Yeah, sorry, it's a direct sum. It's a trees with n leaves, and I would like to decorate trees with the module m. So I would like to say trees of m. Right, it's something of the sort. Is n tensor of m n times, and yeah, so you think of as the module m is attached to the each leaf. Okay, then for any tree T in this trees m, I introduce the grading. Right, so the grade would be the sum of it. Is degree, maybe let's call it T, big T. Degree T is degree of underlying tree, T, plus degree of, maybe start again. Sorry, I would like to write T as a T of A1, AN, okay? Just a tree T with n leaves, and its degree of this tree T is just degree of T plus degree of A1 plus degree of AN. Okay, so up to now it makes sense how to combine these two things together. Okay.
You have A1 through AM. What are you trying to say?
Here?
Yeah.
Yes, so this is a notation I use for a tree decorated by elements A1, AN, and the A1, AN are elements in the module.
They're just
Can you just make a picture?
Yes, so you have tree T, and you write A1, A2, A3, right? So this makes sense if I view this decorated trees like this. So you view trees as a direct sum of trees with n leaves, right? And for each n tree you attach module m. So this A1, A2, A3 are just elements here. Okay. Then the second thing that one wants to do is, of course, symmetrize these trees, because in the Koszul-Tate resolution we are dealing with a symmetry graded algebra. So I would like to symmetrize them. So particularly if you have a tree like T of A1, AN, OT, yeah. Here T of B1, BK. So yeah, so you can just exchange them, right? So you can write the same thing, but exchanged.
Your complex T of trees contained tensor products of trees. And so if you have a tensor product of trees, how do you decorate it with elements in M?
Yeah, so the point is, I mean, so the trees with n leaves, it has some subtrees, right? And I mean, I just read it from left to the right. So I mean, to each subtree there are some elements here. So
Yeah.
Yes. Yes.
Okay.
Yeah, so, and I would like to identify this tree. A1, AN, B1, okay. With some sign, namely just a degree of this T, A1, AN, multiplied by degree of T, B1, okay. And here is this one, okay, one, okay, right. So, for example, yeah. So you quotient by this relation, yeah. So, for example, A1, A2 is identified with -1, A2, A1, A1, right? And if it was some more complicated tree, like this one, maybe here, 1, A2, A3. So this would be, for example, the same tree as A3, 1, A2, with the sign A3, yeah, so put it degree like this. Here, degree A1 plus degree A2 plus 1, because here I also count this this inner vertex that attached to this subtree A1, A2. Okay. So then, after setting this up, so I would like to maybe present what is A in this construction. So move this part. So I would like now to start constructing the differential gradient algebra A in delta. So first I can already specify what is A. So
I couldn't see A at the very.
It's here.
Ah, over there.
Yes.
So is it over? It's not like what.
So the DGA. So first I would specify A, because for delta there is some more input is needed. A would be just a symmetric gradient algebra of these trees. So, and let me maybe first denote trees after taking this quotient. So let's maybe call it tau of M. It's just these trees modulo this quotient, right? Modulo this symmetrization. So the algebra A would be just a symmetric algebra of Tm, right? And given what we already seen about the differential in the space of trees and the differential on the modular resolution, it is tempting to define delta in the following way. So, or at least some of them should be true. So, if you take for trivial trees, so if you take just a trivial tree decorated by M, then delta should reproduce the differential from a modular resolution, right? This would be a very natural thing to do. Okay, so in particular, so elements A would go to elements dA, right? And of course, is A if degree 1, then A would go just to dA. dA is element in F in R. Okay, and then it is tempting to What is it? Unfortunately, I cannot move that blackboard anymore. No. Okay. Okay. Now I think it works. Yeah. Yes.
It doesn't hear you.
D is a differential on M, yes.
That one, okay. And is stays in one.
So A is any element in M, but if A has degree 1, then one should end up in just in R.
M1, M2, this is the degree.
Yes.
Okay.
So if one looks at the differential that was here, so one is tempted to define it as follows. Yes. So the tree disappears. Yes. So one is tempted to define the differential as follows. So there would be a component here, which again, I would like to reproduce this. So let us maybe write R minus 1. There will be a component that sends trees to trees. Which again is recursively defined like this. No, sorry, it's this. Oh. So again, so you reroute, you apply a recursively constructed delta, you project to the space where there are at least 2 tensor trees, or 3 or more, and then you route again with a minus sign. But actually, it's not enough. So there will be down component to the trivial trees, which plays an important role here, and I will explain it now. So one thing that maybe the differential, like here, if one forgets about down component, maybe one thing that maybe it would be enough to just to make it square to 0, but actually it's not. Yes. Yes, it's, but I don't want to write it as a partial. So, because I mean, the partial was just on the space of trees, these are decorated. And I have the whole differential delta here. So it encodes in some way the differential of a modular resolution and the differential of the trees, okay? So let me maybe explain why one needs a new component, which would be constructed which must be constructed separately. So, and the one should make their choices. So let me delete this part and start with a simple tree. Oh. Let me start with a tree AB. Degree of A is equal 1. Degree of B is equal 1. And let me, for a moment, forget about this delta down. So, how delta acts on this AB? Right. So you would have the unrooting, the component which is unrooting the tree. So it's just A tensor B. And then you would like to see what gives component here, right? The one in the middle. So you unrooted this tree. So let me spill it out in the detail. You split it into delta minus 1. So first, you have this maps to this. Second part, you apply delta. So you know how delta acts on the trivial trees, right? So it's just a differential from a modular resolution. And you get, so A, B, it's mapped to DAB minus, let's B, DA, right? I use already this, this thing that the tree disappears when A has a degree 1. B has a degree 1. And then on the step 3, it is 0. Yeah, ADB. And on step 3, you see it's already 0. Right? So you're dealing with just one tree, but you project to the space where there are at least 2 trees, so it's 0. And okay, sure, maybe it's not a problem, but yes, exactly. So it means that the differential delta of this tree is just mapped to this tree, to these 2 trees, A, B, and it doesn't square to 0, because delta square is given by the delta square of this tree. It sends to just DAB minus ADB. Right? So, like naively, if one just combines 2 differential, it doesn't work. Right? But what does work in this particular situation? So the following works. So how I would like to define the component delta down in this situation. So I take an element. I take a tree here. Maybe not just let me just spill it out in full generality, and I go to this particular. Okay. Let me write on the blackboard. So let me write it maybe there already.
Explain like why you need to define this new delta. So
Yes.
Yes.
And I would like to define it and then just to explain this particular situation how to write this. So you start from this decorated trees. You apply this component R-1 component. This. Yes, no tilde. I'm sorry. I just want to write tau as tau with tilde. It's beautiful tau. R projection greater than 2 delta -1. So you end up here. Then you apply delta again here. But actually, one can prove it, and we will see it directly in this. We will see directly in this example that actually you arrive in trivial trees tensor M. Okay. So here, if we in the example above, so here if we applied the separation twice, so I applied this naively defined delta, then I applied delta again, I ended up in a trivial tree like here, right, with some decoration here. And you see that on that tree, delta would square to 0. So you precisely, you arrived in an element, so decoration is an element in a modular resolution, which is manifestly closed, right? If I apply D again to this, then it would be 0. So actually, if here I apply ID tensor D, one can prove that it would be always 0. What it means, because we use the fact that we have a modular resolution, right? That there is actually something here, right? D tensor D. So there is actually a pre-image to this element just using this modular resolution. And I define this map delta down as this. So it's minus down, right? Yes. So of course, you have to choose a pre-image here. So it's not an automatic construction. You have to make choices. Well, but we know it exists, right? And if I define it like this, then the differential delta would be manifestly square to 0. So if this holds, then the differential that's constructed here, it would follow the delta squares to 0. Okay. So
Delta D, is it some kind of contracting homotopy? No? Choosing the pre-image of something which goes to 0 looks like contracting homotopy for me, but I might be wrong.
I don't think so, because there is no contracted homotopy going upwards.
But you choose pre-image.
Yes.
But choosing pre-image, it's pretty close to contracting. I know better.